Hey guys, thank you for joining me again. How many of these videos are you going to watch? Probably too many. But in any case, the topic is energy and chemical systems. And not just energy, enthalpy and work and sign conventions and a few diagrams as well. Question, is it possible for a chemical or physical system, I might add, to involve both heat and work? And the answer is yeah. You know the answer. Because, for example, what happens if I take a hydrogen-oxygen balloon, add a little spark of energy to get the party going, and the whole thing goes kaboom? Some of the sign conventions, so think about that. You've seen it in demonstration, haven't you? Have I shown you? I should have. I hope I have. Hydrogen gas, oxygen gas, very reactive. But it won't do anything until you get it started with a little spark of activation energy. But anyway, that's more for the topic of Gen Chem 2. But anyways, some of the sign conventions are the change in energy of the system is negative. Maybe that's because it releases energy. Maybe that's because the water that's formed has less energy than the reactants. The enthalpy, we say, the delta H change, H is technically for enthalpy, although I commonly refer to it as heat, is also a negative. It seems like E and H are closer related than they are. We say that's exothermic. We also say it's exergic. The work done is actually by the system. The system does the system does work on the surroundings. A whole bunch of work. It's very loud. Our eardrums rattle and shake because of the reaction, because of the outcome. Memorize that. I'll talk about that more in a minute too. Here's a cartoon of a beaker, and it looks like it says Q. The Q is a symbol for heat, and if Q is positive, that implies that heat flows into the system. Yeah, it also implies, well, here's an equation. Q equals M times C times delta T. Have you seen it already in the lab? The heat change, Q, the quantity, is dependent on the mass of stuff involved, the specific heat capacity, and the change in temperature of the water. For water, the specific heat capacity is huge. It's like 4 times bigger at least than any other substance. And delta T is just the change in temperature. Yeah. So I'm not going to use that equation much in this video, but I'm going to assume it's so simple that you can use it. Oh yeah, well maybe I should say, for right now anyway, mass is usually in grams, C is usually in joules per gram degree Celsius, and delta T is in Celsius. If Q comes out negative, that means heat flows out of the system and into the surroundings. Just the opposite. That can be sometimes confusing. Chemists and physicists throw around positives and negatives just to suit seems like to suit their fancy, but it's what everyone's agreed upon to have some kind of meaning. Here's another one to kind of keep in mind. If work is positive, the surroundings do work on the system. For a liquid and a solid, that's not going to do much because liquids and solids aren't much compressible, very much compressible. But gases certainly can be squeezed to a smaller space. In the case of the exploding balloon, this is actually opposite. So work was negative. But in this picture, if I can do work through a force and a distance, that's a physics kind of a work. Excuse me. But there's also something called pressure volume work, which is also, you could argue, physics, but I'm just saying. I'm anxious to get to this silly cartoon I've drawn here in a second. Oh yeah, and opposite of work being positive, work being negative. Excuse me, goodness. Long week, tired of talking. If work is negative, then the system does work on the surroundings. Interesting. Again, not much to imagine there with a liquid or a solid, but if a gas were to expand or to form more moles of gas, that certainly. Here's a stupid picture. I know. You'll make fun of it later behind my back, like you are right now probably. But if you remember this, so here's a system, probably a system of gases. See all the particles inside? And I have a cylinder with a piston that I can push down the plunger. And this stick lady's doing a pushing with a force over a certain distance from here, say, to here, a certain number of newtons, there's a pretty easy way to calculate the work that's being done on the system. The sign convention would be that this work is positive. Also, it must be a fairly sturdy cylinder because I'm heating it from below with a fire, a torch, a candle, or something. The convention is here that Q is positive. I'm adding heat energy into the system. So on both accounts, both Q and W are contributing to the increasing energy of the system. System of gas has more energy than before, so delta E is positive. It gained energy. How does the internal combustion engine compare? Oh yeah. So have you ever studied the operation of an engine? Yeah, I guess a diesel or a gasoline engine. Although the gasoline engine, I'm going to argue, is sort of opposite of this, where I have a system of gases. It is compressed, but right at the time of ignition of the spark plug, then the chemical reaction releases heat energy, and heat energy flows out of, not into, the system. And work is done on the pistons and crankshaft and drive shaft by this chemical reaction expanding quickly outward. So the internal combustion engine would be W negative and Q negative and delta E negative. Yeah. Oh yeah, we saw this equation a moment ago. Mass of substance times the change temperature and the specific heat capacity. Here's a new one for the work. It's, maybe you've watched my other video. The work equals the pressure times volume. And to follow conventions, we throw in a negative there for good measure. Pressure volume work, it's called. Couple of common ways that a system might do work on the surroundings: creating more gas from solids and liquids in a chemical reaction, chemical change, creating more gas, creating increased number of gaseous moles. So if I have some gas but I create more gas, or if I create gas from a solid or liquid, or generating a pressure that causes an increase in the system volume. So if my volume gets larger, it's somehow done some work on the surroundings. Interesting. E is for energy, and so technically if E is positive, we call that endoergic, or if E is negative, we call that exoergic. H is closely related to Q, but work is a separate calculation. The enthalpy and Q are closely related. Maybe I'll say more about that in a minute if I get to it. So these are weird words, strange words. I've heard of endothermic and exothermic. Thermic, thermometer, heat. But more than just that, energy. Energy may involve heat, or it may involve work, or it may involve entropy? Gen Chem 2. Well, whatever. Here's a good question. So if work is done on the system, work is done on the system and heat flows out of the system, technically I call that a negative heat flow, but a positive work, because work's done on the system. So in that sense, the 5 is positive and the 27 is negative, and they add together to be delta E of negative 22 kilojoules. Energy, heat, work often measured in kilojoules, although strictly speaking I suppose the energy is the unit is the joule, but the joule is kind of a small unit, so oftentimes it'll just be reported in kilojoules, which is thousands of joules. Or if I had a system of gases that went from 25 liters to 45 liters, let's see, and it expanded against an external pressure of a constant 10 atmospheres, what's the liter atmosphere work done? W is equal to negative pressure times change in volume. That's just kind of the convention. So the answer would be here, work equals negative pressure times volume. The pressure is 10 atmospheres. Ending minus beginning volume is 20 liters times 10, 200 liter atmospheres. And it might be good for you to know, but we'll probably tell you on the test anyway. The conversion between liter atmospheres of work and joules of work is just this, 101.3 joules per 1 liter atmosphere. That'll become apparent in chapter 7 on gases. Or, in other words, if I had that 200 liter atmospheres of work, I can change it to joules, 20-ish kilojoules. What else should I say? Another example. Interesting. Should I? Let's see, what's new here? Liter atmosphere, the volume goes from 15 to 45. The pressure is 2, 30 kilojoules. 30 kilojoules of heat flows from the surroundings. If you were brave, you could pause the video right now and try this yourself. Or there you go. Here are the conventions. It looks like, what did it say? It says heat flows from the surroundings into the system. That's a positive Q. And it expands from 15 to 45. That's a negative W. I'm predicting. Look, I think I'm right. So ending minus beginning is positive, but I throw in a negative there. Really, this should have a delta E there. Oh, well, getting lazy with my deltas. I have another video on state functions and path functions. Here are some interesting definitions that might serve us well in the future for enthalpy change. We almost go products minus reactants. And delta H and Q are closely related, although delta H is usually reported in kilojoules per mole. And also you got to be careful with the sign convention about, am I talking about the system or am I talking about the surroundings? The change for the surroundings is always the opposite of the change for the system. So the system might be positive or negative Q or W in some sense, but the surroundings are actually opposite that because they interact and give or take heat and work. Don't lose much sleep over those definitions, but it's good to think about for now. What? Did I have a question here, or what am I doing? Interesting. So heat goes into the system, endothermic, and the pressure volume work. I honestly don't know where those numbers came from. Whatever. Another example. So again, what does H tell us? Delta H, the enthalpy. It is B, the heat flow at a constant pressure. So us chemists are pretty simple-minded, and we like to assume the pressure of the atmosphere is the pressure in the laboratory, is the pressure in our simple system, and we're considering that pressure not to change much. If it does, the enthalpy change, delta H, might have been affected, but such a small amount, we're assuming it'll be close to nil. Here's a cool endothermic reaction with barium hydroxide and ammonium thiocyanate. Maybe I'll show you this demonstration. I will show you this demonstration, and maybe I'll talk about the energetics as well. But if barium hydroxide and ammonium thiocyanate react endothermically, see that positive delta H, then I think I take 15 grams of ammonium thiocyanate and a little conversion. So if I change 15 grams of this chemical into moles with the molar mass, and then use the 2 there in relation to the 165 kilojoules, I can actually do a calculation, right, about how much energy would be taken in if I did react 15.5 kilograms, 15.5 grams of this white powdery chemical with as much barium hydroxide as I want. Kind of draw an energy level diagram like this, where the reactants are low in energy and the products are high in energy. This is actually kind of slightly more rare in most inorganic scenarios, a slightly more rare reaction. Usually they go the other way. Do you know what I mean by that? Oh, do you know where this came from? Where this conversion came from? I know how to change grams to moles, but didn't it say 165 kilojoules was associated with 2 moles of ammonium thiocyanate from the balanced thermochemical equation? Yeah. So 15.5 times 165 divided by 76.2 divided by 2 should give me close to 17 kilojoules absorbed. Oh yeah, right. Okay, good. The opposite of increasing in energy is decreasing in energy, like the reactants are high in potential and they fall down the energy hill. And lo and behold, one of my favorites is the thermite reaction, where I have rust and aluminum, and the rust and aluminum are high in energy. The aluminum oxide and iron are lower in energy, and the difference between here and here is quite a bit, very exothermic. I did a calculation. I said if I had 20 grams of aluminum, I changed grams to moles, then I compare 2 moles of aluminum in the balanced equation, 2 moles of aluminum to the negative 848 kilojoules. Do the math, and it comes out to 314 kilojoules. So yeah, rarely would I use a full mole of rust and a full 2 moles of aluminum. That would be a huge reaction. Oh yeah, and this is exothermic because I start high and low, but I do have to get up over the activation energy barrier, which can be difficult. Alright guys, thanks for watching. Have a good one. See you in class.